The odds of Thruai Atlas randomly passing this close to 3 planets in a single flyby, roughly 1 in 20,000. Now, the odds of it doing that while perfectly aligned with the ecliptic plane, the flat disk where almost all of the solar system's mass orbits, jump even further, add 3 more zeros, and the probability that these encounters happen at exactly the right distances and velocities to allow for gravitational assists as if the object were intentionally adjusting its trajectory, at that point, the math just stops making sense, unless someone planned it. It passed Mars on October 3rd, just 35 days ago, at a distance of 45 million kilometres, close enough that every spacecraft orbiting Mars should have captured detailed images. In late December, about 7 weeks from now, it's projected to approach Venus at around 30 million kilometres. Then, in mid-January 2026, it will swing past Jupiter, coming within 150 million kilometres, 3 planets, 3 encounters, and every single one happens at just the right range and speed to provide a gravitational boost if, and that's a big if, Atlas were trying to change its course. Now here's where things start to get really strange. Natural interstellar objects just don't behave like this. When Oumuamua passed through the solar system in 2017, it came in at a steep 26-degree angle above the ecliptic plane and left without any close planetary encounters. Tusai Borisov, discovered in 2019, followed a similar path, cutting through the inner solar system at an inclination that kept it safely away from every planet. That's what we expect from interstellar visitors, random trajectories, coming from arbitrary directions in 3-dimensional space. But 3 Atlas, it's different. Its path lies almost perfectly within the ecliptic plane, tilted by only 2 degrees from the flat disk where Earth, Mars, Venus and Jupiter orbit. That means Atlas moves exactly through the region where planets reside, maximising its chances of close encounters. And these aren't random passes at arbitrary distances. Each encounter occurs at a range that allows for meaningful gravitational influence, the same kind of precision mission planners use when designing spacecraft trajectories. We've just gone over the orbital mechanics, the probability math behind those 3-planet encounters, and the gravitational assist patterns that make Atlas's trajectory look a lot less like an accident and a lot more like intentional design. Now, we're going to break down what it actually takes to plan a multi-planet trajectory, why Atlas's perfect ecliptic alignment is so unlikely for a natural object, and what it would mean if it's using planetary flybys to steer its course through the solar system. Because whether you see this as an astronomical coincidence or evidence of deliberate navigation, one thing's crystal clear: the numbers are too precise, and the alignments are too perfect. If this path was designed, then someone or something calculated it long before Atlas ever reached our solar system. Alright, let's dive in. But before we do, if you enjoy deep space investigations like this, hit that like button, subscribe, and let me know in the comments where you're watching from, what time it is there, and whether you think Atlas's trajectory is random chance or mission architecture. The Mars encounter on October 3rd was the first real test of whether Atlas's trajectory is a product of nature or of design. Close approaches between interstellar objects and planets are extremely rare. Space is unimaginably vast, and planets are tiny targets in comparison. Mars's gravitational sphere of influence, the zone where its gravity outweighs the Sun's, extends about 500,000 kilometres from its centre. Atlas passed at 45 million kilometres, roughly 90 times farther out. Still, that's close enough for Mars's gravity to cause a measurable deflection. When an object passes near a planet, that planet's gravity tugs on it, subtly changing its velocity. The closer the pass, and the slower the speed, the greater the effect. For Atlas, sweeping past Mars at 40 kilometers per second, the change in velocity would be only a few meters per second, a tiny fraction of its total speed. But in the emptiness of interstellar space, even small changes add up. Over months or years, those few meters per second can shift the path enough to determine where the object goes next. That's the same principle behind gravitational assists, a cornerstone of modern spaceflight. Voyager 2, launched in 1977, used a chain of flybys Jupiter, Saturn, Uranus, Neptune to reach the outer edges of the solar system. Each encounter bent its path, giving it a slingshot of extra speed toward the next planet. The mission's entire design, the launch timing, the route, the flyby distances, was meticulously planned to take advantage of those assists. Without them, Voyager would never have reached Uranus or Neptune. Those gravitational boosts weren't luck. They were calculated years in advance. Atlas's trajectory shows the same fingerprints as a planned mission. The October 3rd Mars encounter occurred at just the right angle to bend Atlas's path slightly inward, nudging it toward Venus. Without that deflection, it would have passed Venus at a far greater distance. With it, the December encounter becomes possible. Then, that Venus flyby, if it happens as predicted, will redirect Atlas toward Jupiter, setting up the January 2026 approach. Each step enables the next, forming a chain of gravitational assists almost identical to Voyager's grand tour of the outer planets. But here's the catch. You can't design a path like that without foresight. To plan such a sequence, you'd need to know exactly where the planets will be years, if not centuries in advance. Atlas entered the solar system from interstellar space, coming roughly from the direction of the constellation Hercules. For it to reach Mars on October 3rd, 2025, at just the right distance and velocity to set up the Venus deflection, its trajectory had to be established long before it ever reached the solar system's edge. Once an object falls under the sun's gravity, there's no easy way to change course, not without powerful propulsion. The trajectory is effectively locked in by the time it crosses Neptune's orbit, which raises a troubling question. If Atlas's path was fixed that far out, who or what set it in motion so precisely? This means that whoever or whatever set Atlas's trajectory had to know far more than just where it was headed. They would have needed to calculate in advance where Mars would be on October 3rd, 2025, where Venus would be in late December 2025, and where Jupiter would be in January 2026, all from a starting point light years away. Now yes, planetary positions can be predicted with orbital mechanics, but doing so requires precise data, the orbital parameters, masses, and reference time positions of the planets. That's the kind of information used in mission planning, not the byproduct of natural chaos. Gravity doesn't plan ahead. A rock ejected randomly from another star system doesn't fine-tune its path to intersect planets decades in the future. Astrophysicist Avi Loeb ran the numbers. He calculated the probability of a random interstellar object encountering 3 planets within gravitationally significant distances during a single trip through the inner solar system. Starting with the assumption that such objects approach from random directions, evenly distributed across the sky, he found that most would pass through the solar system at steep angles, far from the flat plane where planets orbit. Only about 10% would ever come within 10 degrees of the ecliptic, and less than 1% would align within 2 degrees, as Atlas does. In other words, the odds of 3i Atlas's path being purely random are vanishingly small. So, the prior probability that an interstellar object would even align with the ecliptic plane is about 0.1%. That's roughly 1 in 1,000. Now, add the requirement that it also passes within 50 million kilometers of Mars. Mars's orbital path is around 3 billion kilometers in circumference, and the segment where Atlas passes close enough for a near encounter covers about 100 million kilometers, just 3% of that orbit. Multiply those two probabilities, 0.1% x 3%, and 0.003%. That's about 3 in 100,000. Next, bring Venus into the picture. Its orbit is tighter, about 700 million kilometers around, with a close approach window of 60 million kilometers, or 8% of its orbit. The chance that a Mars-encountering object also passes near Venus becomes 0.003% x 8%, 0.024%, roughly 1 in 400,000. Now add Jupiter. Its enormous orbit spans about 5 billion kilometers, and an encounter zone within 200 million kilometers makes up 8% of that circumference. Multiply again, 0.024% x 8% down 0.019%. That's about 1 in 5 million. And that's before considering how precisely these encounters occur. This calculation assumes the object passes randomly within those encounter zones. But Atlas's flybys happen at near-optimal distances for gravitational assists, close enough to cause meaningful deflection, but not so close as to risk instability or collision. Once that constraint is added, Loeb's final estimate puts the odds at roughly 1 in 20 million. Those are lottery-winning odds, the kind of astronomical coincidence that pushes scientists to ask whether coincidence is really the right explanation. To understand why Atlas's trajectory raises so many eyebrows, you first need to grasp how gravitational assists, also known as gravity slingshots, actually work, and why spacecraft engineers spend years designing missions around them. A gravitational assist isn't magic, it's orbital mechanics used with precision. When a spacecraft approaches a planet, the planet's gravity pulls it inward, accelerating it. As the craft swings around and departs, gravity pulls it back, decelerating it by the same amount. In the planet's own frame of reference, it leaves with the same speed it arrived, no energy gained, no energy lost. But here's the clever part. Planets are moving. Earth orbits the Sun at about 30 kilometers per second. Jupiter moves at around 13 kilometers. If a spacecraft approaches a planet from behind, moving in the same direction as the planet's orbit, it can steal a bit of the planet's momentum, speeding up in the Sun's frame of reference. Approach from ahead, and it gives momentum back, slowing down instead. The planet's speed barely changes. It's far too massive to notice, but for the spacecraft, the velocity shift can be huge. Voyager 2 is the classic example. It used a sequence of gravitational assists to tour the outer solar system. At Jupiter, it approached from behind, gaining speed and bending its trajectory towards Saturn. Then Saturn's pull redirected it toward Uranus, and Uranus toward Neptune. Each encounter added energy, propelling Voyager to speeds rockets alone could never achieve. By the time it left Neptune in 1989, Voyager was moving fast enough to escape the solar system entirely, now coasting through interstellar space at roughly 15 kilometers per second relative to the Sun. That kind of precision doesn't happen by chance. It's the result of deliberate planning and exact timing, and that's exactly what makes Atlas's path so hard to dismiss as random. Designing a multi-planet mission like Voyager's requires an astonishing level of precision. When Voyager launched in 1977, its window of opportunity was only a few weeks long. Launched too early or too late, and the probe would have missed Jupiter's position by millions of kilometers, ruining the chance for the gravity assist that would send it towards Saturn. Every leg of the journey depended on predicting planetary positions years ahead of time, threading the spacecraft through space with timing accurate to within hours. NASA's engineers spent years running those calculations on the most powerful computers of the 1970s. The result, Voyager's grand tour of the outer planets, remains one of the great triumphs of orbital mechanics, a masterpiece of human ingenuity and foresight. Now consider 3I Atlas. If its trajectory is truly designed, then whoever or whatever planned it accomplished something on par with Voyager's mission, but on a cosmic scale. Atlas didn't launch from Earth. It approached the solar system from interstellar space, travelling for perhaps millennia before reaching us. Yet to arrive at Mars on October 3, 2025, within 45 million kilometres and at the exact velocity needed for a gravitational deflection toward Venus, its trajectory had to be preset long before it crossed Neptune's orbit. And to set that trajectory with such precision, the planner would have needed to know where Mars would be on that exact date, decades or even centuries in advance. Mars completes one orbit around the Sun every 687 days, and its position at any given time can be predicted with remarkable accuracy using Kepler's laws of planetary motion. But those predictions depend on having a reference point, a precise starting epoch that marks where Mars was at a known moment in time. From that point, astronomers can project its motion forward or backward. Here's the problem. If 3I Atlas truly originated from another star system, and if its course was set decades or even centuries ago, then whoever designed it would have needed either incredibly precise, long-range observations of our solar system, or prior knowledge perhaps from previous visits. Now, long-range observation is possible. A sufficiently advanced civilization with powerful optical telescopes could detect planets around nearby stars and measure their orbital periods, eccentricities and inclinations. With years, maybe decades of observation, they could construct detailed models of each planet's orbit, just as we do when studying exoplanets. But even with advanced instruments, there are limits. From light years away, our planets are tiny, faint points of reflected sunlight, barely distinguishable from the glare of the sun. Measuring their exact positions with the precision required to plan a multi-planet flyby would be extraordinarily difficult. It would demand continuous monitoring across multiple orbital periods, several years for Venus and Mars, and decades for Jupiter. And it doesn't stop there. To predict planetary positions decades into the future, the calculations must also account for orbital perturbations, the subtle gravitational tugs planets exert on each other over time. Jupiter's gravity slightly shifts Mars's orbit. Venus influences Earth's. These effects are tiny but cumulative, and ignoring them would throw off a precise trajectory. In short, designing Atlas's path from interstellar space would require a level of astronomical modelling far beyond what nature or chance could produce. It would take either an extraordinarily advanced observer or someone who's been here before. If Atlas's trajectory was truly designed from interstellar space, then it represents a level of observational and computational power that goes far beyond anything humanity has ever achieved. We can predict the positions of planets in our own solar system with extraordinary precision, but only because we've been observing them for centuries, and because we now have spacecraft and probes scattered throughout the system sending back real-time data. Designing a precise multi-planet trajectory from light years away, without that local information, is a challenge on a completely different scale. It's possible in theory, but it would demand a civilization with technology, patience and precision that vastly exceeds our own, someone capable of mapping orbital dynamics to the meter across decades from another star system. But there's another explanation, one that's just as intriguing. What if Atlas didn't plot its course from interstellar space at all? What if it's been making adjustments since it entered the solar system? That would require onboard propulsion, the ability to fire thrusters and alter its velocity in small but precise increments. Even tiny course corrections on the order of just a few meters per second can make an enormous difference over time, fine-tuning the trajectory so that planetary flybys occur exactly as planned. It's the same principle that guided Voyager. While its major maneuvers came from gravitational assists, it also carried thrusters used occasionally to correct small deviations, compensate for gravitational uncertainties, or target specific features on a planet during flybys. Those corrections were minor, but essential. They kept the mission on track across billions of kilometers. So if Atlas is capable of similar corrections, it wouldn't need to know the future from light years away. It would simply need the ability to adapt once it arrived. And that possibility changes everything. If Atlas does have onboard propulsion, then two events become very interesting: the green emission on September 7th and the maneuver window around perihelion on October 29th. A small burn in early September could have shifted Atlas's arrival at Mars by just a few hours, making sure the October 3rd flyby happened at the exact distance needed to bend its path toward Venus. A second burn near perihelion, when its speed was highest and the Loeb effect makes every bit of thrust more efficient, could have been used to fine-tune the December Venus encounter. The problem is, burns that small are almost invisible. If you only model Atlas with gravity, the trajectory looks perfectly normal. To spot propulsion, you have to compare where Atlas should be to where it actually is. Even a 1 meter per second change in velocity will move the object about 600 kilometers over a week. At Atlas's current distance, that shift is roughly the same size as the uncertainty in our measurements. That's why the teams analysing its orbit right now are getting inconclusive results. We either need more precise tracking, or we need to wait long enough for the tiny corrections to add up and become undeniable. The important thing to understand is that this whole Mars-Venus-Jupiter sequence doesn't actually require Atlas to be firing engines all the time. If the original interstellar approach was designed correctly, the planetary flybys can be built into the trajectory from the beginning, with only small corrections needed along the way. That's exactly how Voyager was planned. The route was robust. Even if one gravity assist wasn't perfectly efficient, the spacecraft would still reach most of its targets. In Atlas's case, the Mars flyby on October 3rd was far from the planet, about 45 million kilometers, but even at that distance, Mars's gravity can change Atlas's velocity by roughly 3 meters per second. That's tiny compared to its overall speed, but in orbital mechanics, tiny changes made early lead to huge differences later. Over the following weeks, that small deflection is enough to bend Atlas's path slightly inward, bringing it closer to the Sun and lining it up for the Venus encounter. The Venus encounter in late December is the real pivot point. It's much closer, about 30 million kilometers, and because Venus is more massive than Mars, its gravity packs a stronger punch. Depending on the exact geometry, the deflection could reach 20 meters per second. That might not sound dramatic, but in the slow ballet of orbital mechanics, a 20 memis shift is huge. Over the course of a few months, that small nudge can move an object's position by millions of kilometers. If the deflection tilts in the right direction, it steers Atlas straight toward Jupiter. If not, Atlas misses the giant planet entirely and slips back into interstellar space. Then comes the Jupiter encounter in January 2026, the heavyweight of the sequence. Jupiter, with a mass 318 times that of Earth, dominates the outer solar system. Even a flyby at a distance of 150 million kilometers, a long way by planetary standards, can bend Atlas's velocity by 50 to 100 meters per second, depending on the angle of approach. That's an enormous change compared to the earlier encounters. And this is where the idea of a design trajectory becomes unmistakable. If Atlas approaches Jupiter from precisely the right vector, that encounter could rewrite its path entirely, sending it deeper into the solar system for additional flybys, flinging it outward at interstellar escape speed, or even capturing it into a long looping solar orbit. In mission design terms, Jupiter is the decisive maneuver, the moment that reveals whether Atlas is simply passing through or following a plan. Astrophysicist Avi Loeb has already modelled several possible outcomes for the Jupiter encounter, each depending on the angle of approach, and the differences are dramatic. If Atlas approaches from behind, moving in the same direction that Jupiter orbits the Sun, Jupiter's immense gravity could act like a cosmic slingshot. In that configuration, Atlas would gain energy, picking up speed and leaving the solar system at a much higher escape velocity than it had when it arrived. It would exit on a new outbound trajectory, effectively using Jupiter as a launch platform to propel itself back into interstellar space. But if Atlas comes in from ahead, meeting Jupiter head-on, the effect reverses. Jupiter's gravity would drain momentum from Atlas instead, slowing it down in the Sun's reference frame. That deceleration could be enough to trap the object in a long elliptical orbit around the Sun, turning what might have been a fleeting interstellar visitor into a permanent member of the solar system. Which scenario actually plays out will depend on the fine details of the Venus flyby and the resulting changes in Atlas's velocity and direction. Those details won't be clear until late December, when we finally see where Atlas is headed after its Venus encounter. That's when we'll learn whether it's preparing to slingshot away or settle in for the long haul. This lingering uncertainty about what Atlas will actually do next is both frustrating and electrifying. If Atlas's trajectory really is designed, then the Jupiter encounter will be the moment where that design becomes impossible to ignore. Natural interstellar objects don't carefully orchestrate their approach to Jupiter to produce a specific outcome. They simply follow the geometry fate gives them, but a planned trajectory could aim for an exact approach vector, choosing whether to accelerate outward, slow down into a bound orbit, or even set up a return path decades from now. That's why the December Venus encounter is so critical. It's the last major checkpoint before the big test. If astronomers can measure Atlas's position and velocity in early January 2026, after the Venus flyby but before the Jupiter approach, they'll be able to predict exactly where and how the Jupiter encounter should happen. Then comes the real test. If the observed deflection matches a trajectory that looks deliberately optimized, it will be hard to explain away as coincidence. It would strongly suggest intentional navigation. But if the geometry turns out to be random consistent with a natural object drifting through on a chance alignment, then the coincidence hypothesis survives another round. Either way, the data from December and January will decide the story. This is where speculation ends and evidence takes over. The ecliptic plane is the key to understanding just how extraordinary Atlas's trajectory really is. The ecliptic isn't just an arbitrary line. It's the fundamental plane of our solar system, the flat disk where Earth orbits the Sun, and by extension, where nearly all major planets reside. Every planet stays remarkably close to this plane. Mercury's orbit is tilted by about 7 degrees, Venus's by 3.4, Mars's by 1.9, and Jupiter's by just 1.3 degrees. Those are tiny numbers on a cosmic scale, and that alignment isn't coincidence, it's a direct consequence of how the solar system was born. Roughly 4.5 billion years ago, the Sun was surrounded by a swirling disk of gas and dust. As gravity pulled material inward, rotation flattened the cloud into a thin, spinning sheet, a cosmic pancake. Within that disk, dust grains clumped together, forming larger and larger bodies. Over time, collisions built the planets, and because they all formed from the same flattened structure, they inherited its geometric flatness. The result is that about 98% of the solar system's total mass, the Sun, the planets, and nearly everything that matters gravitationally, exist within a thin layer only a few degrees thick. This is the ecliptic plane, the solar system's invisible foundation, the stage on which all its major dynamics unfold. And that's what makes Atlas's near-perfect alignment with it so remarkable. For a visitor from interstellar space, an object that should be coming from a random direction in three-dimensional space to thread itself into this narrow gravitationally active plane is not just unusual, it's statistically staggering. Objects that form within the solar system like asteroids and comets tend to stay close to the ecliptic plane because they were born from the same flattened disk of material. Over billions of years, the combined effects of gravity and collisions have continually nudged their orbits into that thin, organised layer. Most asteroids orbit within 20 degrees of the ecliptic. Most short-period comets, which circle the Sun in less than 200 years, stay within about 30 degrees. The gravitational pull of the planets acts like a cosmic sculptor, smoothing out the chaotic three-dimensional motions that once existed. The solar system is flat because gravity erases randomness over time, but interstellar objects are different. They don't share this origin story. They come from other star systems, ejected by the powerful gravitational kicks of massive planets or binary stars. When one of these encounters happens, the object is flung out into interstellar space along a random trajectory, the result of the exact geometry and timing of that ejection. Once free, the object drifts through the galaxy in a straight line, unaffected by any significant gravity except the faint collective pull of distant stars. When it eventually crosses paths with another star system, ours for example, it approaches from whatever direction it happened to be travelling. There's no physical reason for that direction to line up neatly with the ecliptic plane of our solar system. Statistically, most incoming interstellar visitors should arrive at steep angles, diving through the solar system and out again without ever interacting closely with any planet. That's why Atlas's near-perfect alignment with the ecliptic within just a couple of degrees is so unusual. It's behaving less like a random visitor, and more like something that was aimed. Umama gave us the textbook example of what a natural interstellar visitor should look like. When it passed through the solar system in 2017, it came in at an inclination of about 26 degrees above the ecliptic and departed at roughly the same angle. Its path sliced sharply through the solar system's plane, never lingering near the orbits of the planets. That steep tilt is exactly what you'd expect from an object ejected randomly from another star system. It had no connection to our solar system's architecture and no reason to align with it. Then came Tui Borisov in 2019, and it followed the same pattern, only more extreme. Its approach angle was about 44 degrees, an even steeper descent through the ecliptic. Borisov's trajectory took it straight through the inner solar system, but well above and below the planetary orbits. It passed 300 million kilometers from Mars and 200 million kilometers from Earth close in astronomical terms, but far too distant for any meaningful gravitational interaction. It came in fast, at over 30 kilometers per second, swept through and exited almost unchanged. Both Oumuamua and Borisov behaved exactly as orbital dynamics predict for random interstellar objects, tilted, transient and detached. They were cosmic passers-by unbound, unaffected and uninvolved. Which makes Atlas's trajectory, lying almost perfectly within the ecliptic and threading between planets, all the more extraordinary. Oumuamua gave us the textbook example of what a natural interstellar visitor should look like. When it passed through the solar system in 2017, it came in at an inclination of about 26 degrees above the ecliptic and departed at roughly the same angle. Its path sliced sharply through the solar system's plane, never lingering near the orbits of the planets. That steep tilt is exactly what you'd expect from an object ejected randomly from another star system. It had no connection to our solar system's architecture and no reason to align with it. Then came 2I Borisov in 2019, and it followed the same pattern, only more extreme. Its approach angle was about 44 degrees, an even steeper descent through the ecliptic. Borisov's trajectory took it straight through the inner solar system, but well above and below the planetary orbits. It passed 300 million kilometers from Mars and 200 million kilometers from Earth close, in astronomical terms, but far too distant for any meaningful gravitational interaction. It came in fast, at over 30 kilometers per second, swept through, and exited almost unchanged. Both Oumuamua and Borisov behaved exactly as orbital dynamics predict for random interstellar objects, tilted, transient and detached. They were cosmic passers-by, unbound, unaffected and uninvolved. Which makes Atlas's trajectory, lying almost perfectly within the ecliptic and threading between planets, all the more extraordinary. This entire probability argument rests on the assumption that interstellar objects approach from truly random directions, that their arrival directions are isotropic, spread evenly across the sky. But in reality, the galaxy isn't perfectly uniform. There are subtle directional biases. Most stars, including those that could eject interstellar debris, lie within the galactic disk, a relatively thin layer of stars surrounding the Milky Way's centre. That means interstellar objects are slightly more likely to approach from directions close to the galactic plane, which in turn might produce a minor excess of low-inclination trajectories when they enter our solar system. But that effect is weak, only a few percent at most. It can't come close to explaining Atlas's near-perfect 2-degree alignment with the ecliptic. Avi Loeb explored this by comparing Atlas to the only two confirmed interstellar objects before it, Oumuamua and 2I Borisov. 3 objects, 3 inclinations, Oumuamua 26 degrees, Borisov 44 degrees, Atlas 2 degrees. The sample is admittedly tiny, too small for rigorous statistics, but it's still revealing. If interstellar visitors were truly random, we'd expect most to come in at steep angles, well above or below the ecliptic because random geometry favours high inclinations. In that case, seeing 2 out of 3 with steep inclinations fits the expectation perfectly. But Atlas, at just 2 dig, sits in the extreme tail of that distribution, the kind of alignment you'd expect in less than 1% of random cases. Statistically, it's an outlier. Dynamically, it's suspicious. And in the context of everything else we've seen, the planetary flybys, the precision of the timing, it's the one detail that keeps astrophysicists wondering whether coincidence is still the simplest explanation. Avi Loeb ran the numbers to see just how improbable Atlas's alignment really is. If interstellar objects arrive from random directions, the odds that a random sample of 3 would include even one object with an inclination below 2 degrees is about 6%. That's not impossibly rare, but it's rare enough to make astronomers pause. Now add another condition, that this same low-inclination object also encounters 3 planets within gravitationally significant distances during a single pass through the solar system. When you combine those probabilities, the likelihood plummets to less than 0.1%, roughly 1 in 1,000. Those are the odds that Atlas's entire trajectory is just a coincidence, a product of natural motion with no design behind it. There's another way to look at it, a more intuitive one. Suppose you were designing a mission to explore the solar system using gravitational assists, aiming to visit multiple planets or adjust your trajectory along the way. Where would you target your spacecraft? You'd aim for the ecliptic plane, because that's where the planets are. It's the cosmic highway that connects every major world. A trajectory steeply inclined to the ecliptic might get you one planetary encounter, maybe two if you're lucky, but it spends most of its time above or below the region where planets orbit. In contrast, a path that hugs the ecliptic maximizes the chances of multiple close encounters, allowing for a chain of gravitational assists, the kind of sequence Atlas appears to be following. So when you look at it that way, the logic becomes clear. If Atlas's path were engineered for efficiency, it would look exactly like this. If it were random, it almost certainly wouldn't. A trajectory aligned with the ecliptic is like travelling along the main highway of the solar system. It keeps you in the narrow disk where all the planets orbit and maximizes encounter opportunities. That's exactly why every major interplanetary mission we've ever launched, Voyager, Cassini, New Horizons, has followed a path close to the ecliptic plane. It's not just because our launch sites happen to sit near Earth's equator, which itself lies close to the ecliptic. It's because this alignment is the most efficient way to encounter multiple planets. Mission designers choose ecliptic trajectories on purpose. They know that travelling along the plane of the planets gives them access to the natural gravitational assists that make multi-planet missions possible. It's deliberate, not coincidental. Atlas's trajectory shows the same pattern. It's moving almost exactly within the ecliptic despite being an interstellar object, not something born from our solar disk. That's what makes it so striking. If someone or something designed this path, a low-inclination orbit would be the rational choice. It's the most efficient configuration for a sequence of planetary encounters. The fact that Atlas's inclination is just 2 degrees isn't random, it looks strategic. But there's also a reasonable counter-argument, one that astronomers have been quick to point out: observational bias. Maybe Atlas isn't special, it's just the kind of object we're most likely to notice. Here's why. We detect interstellar objects only when they pass close enough to the Sun to reflect enough light for our telescopes to see. And our telescopes, especially those searching for asteroids and comets, spend most of their time scanning the ecliptic plane, because that's where almost everything local, the asteroids, comets and planets, tends to be. So, if an interstellar object happens to approach at a low inclination, it naturally spends more time near the ecliptic where our instruments are watching. A high-inclination object might zip through the outer solar system far from our line of sight, never bright enough to register. That means we could be seeing a detection bias. Our surveys are more sensitive to low-inclination visitors, giving the impression that such alignments are more common than they really are. In short, there are 2 possibilities. Either Atlas's alignment is intentional and strategic, the signature of design, or it's the product of where we're looking, an artifact of our own observational habits. The challenge is figuring out which explanation fits the data better. This counter-argument does make sense at first glance. After all, most survey telescopes do focus heavily on the ecliptic plane, since that's where the majority of asteroids and comets reside. Statistically, it's the most efficient place to look if you're searching for solar system objects. So yes, there is a built-in bias toward detecting low-inclination bodies, but that bias isn't nearly strong enough to explain Atlas. Modern wide-field surveys like Pan-STARRS, the Catalina Sky Survey, and now even Atlas itself routinely scan large portions of the sky, far beyond the narrow strip of the ecliptic. These instruments have discovered hundreds of high-inclination asteroids and comets, including some on retrograde orbits objects moving opposite the planet's direction of motion. That alone proves the point. Our detection systems aren't blind to high-inclination trajectories. If interstellar objects with steep approach angles were common, we would have found more by now. And in fact, the 2 confirmed interstellar visitors before Atlas, Oumuamua and Tuwaya-Borisov, demonstrate exactly that. Oumuamua, with its 26-degree inclination, was already well above the ecliptic when Pan-STARRS spotted it in 2017. Borisov, discovered at an even steeper 44 degrees, was far off the ecliptic as it crossed the inner solar system, yet telescopes tracked it easily. So we can detect high-inclination interstellar objects. We've already done it twice, which means Atlas's 2-degree inclination isn't the product of a blind spot in our surveys. It's genuinely different, a low-inclination interstellar visitor whose trajectory aligns almost perfectly with the solar system's planetary plane. And that's what makes it so intriguing. The previous 2 visitors behaved like natural drifters from random directions, while Atlas looks like it knows where it's going. There's also the matter of timing, and it's one of the most striking coincidences in Atlas's entire path. The object crossed the ecliptic plane, the precise point where its trajectory passes from below the solar system's disk to above it, in late September 2025, just days before its October 3rd Mars encounter. That means Atlas wasn't just aligned with the ecliptic, it was moving through the densest region of the planetary disk at exactly the moment it passed near Mars. In a random trajectory, there's no reason for those 2 events, the ecliptic crossing and a planetary encounter, to coincide so neatly. The crossing could have happened anywhere along its path, weeks or months before or after Mars's orbit. The fact that it happened right there, right then, looks less like coincidence and more like coordination. It's like threading a cosmic needle. The ecliptic plane is the eye of that needle. The planets are threads running through it, each following its own orbit. And then comes Atlas, another thread drawn from deep space passing through the same eye at the exact moment one of the planetary threads, Mars, also crosses that point. Now imagine doing it again with Venus just weeks later, and then again with Jupiter in early 2026. Each alignment compounds the improbability. The chance that 2 threads cross the eye together is already low. The chance that 3 or 4 do so, each timed precisely within weeks of one another, is astronomically small. If you were designing a trajectory to maximize gravitational encounters, you'd want those crossings to happen this way timed perfectly, as the object passes through the ecliptic near key planets. If it's random, it's one of the luckiest alignments ever recorded. If it's not, then someone threaded that needle on purpose. Loeb's analysis puts hard numbers to what intuition already suggests. He calculated the odds that a randomly oriented interstellar trajectory would happen to cross the ecliptic plane within 30 days of when Mars crosses it, 90 days of when Venus does, and 120 days of when Jupiter does. The combined probability, roughly 0.001%, about 1 in a million. Those are the chances that Atlas's trajectory with its near-perfect ecliptic alignment and its precisely timed planetary encounters happened entirely by accident. Now, 1 in a million odds don't prove design. Science doesn't work on certainties that clean. But probabilities like this do something just as important. They shift the burden of explanation. When multiple low-probability events align, when geometry, timing, and dynamics all line up perfectly, it becomes harder to keep calling it coincidence. At that point, the intentional explanation starts to look not only plausible, but elegant. If Atlas's path was planned, the logic fits neatly together. The ecliptic alignment wasn't random, it was chosen to enable planetary encounters. The sequence Mars, then Venus, then Jupiter wasn't luck. It was engineered to use gravitational assists for controlled trajectory changes, and the timing crossing the ecliptic exactly as the planets do was part of the mission design, not a happy accident. In other words, the simplest explanation for so many aligned improbabilities is intentionality. Someone or something wanted Atlas to fly this path. Now everything comes together. The triple planetary flyby, the precise ecliptic alignment, the gravitational assist geometry, each piece reinforces the same conclusion. If Atlas's trajectory was designed, then whoever or whatever created it must have performed those calculations long before it entered our solar system. That level of foresight demands knowledge, capability, and intent far beyond anything natural processes can generate. So what would a mission design even look like when you're approaching not from a nearby launch pad, but from interstellar space? And what can the upcoming December and January encounters tell us about what Atlas is actually trying to do? Designing an interstellar probe is a completely different challenge from planning a mission within a solar system. When NASA plans a mission to Jupiter or Saturn, the starting conditions are well defined. the spacecraft launches from Earth, whose position, velocity, and timing are known to extraordinary precision. Engineers can then calculate where every planet will be years in advance, using those known reference points to design a precise trajectory-optimizing launch windows and flybys with accuracy measured in kilometers and seconds. The Voyager missions are the perfect example. They took years to design, not because the math was uncertain, but because the opportunities were rare. The geometry that allowed Voyager to visit Jupiter, Saturn, Uranus, and Neptune in a single sweep occurs only once every 176 years. But all of that planning happened within one solar system, under conditions we understood perfectly. Every orbit, every gravitational field, every planet's position mapped and verified. Now imagine attempting that same level of precision from light years away, with no local data, no infrastructure, and no chance to correct major errors once the probe is in motion. That's what makes Atlas's trajectory so hard to dismiss. It doesn't just look planned, it looks like the product of mission-level design, executed from beyond the Sun's domain. An interstellar mission doesn't get to start with a perfect map. If you're launching from your star system toward our solar system, all you have to work with at first are telescopic observations across light years. You can see the Sun. You can measure its proper motion. With good instruments and enough time, you can even detect some of its planets. Jupiter is easiest, maybe Saturn, maybe hints of Earth or Venus through transit or radial velocity signals. From that, you can estimate orbital periods, semi-major axes, inclinations, but you can't know them as precisely as we do from inside the solar system. Even with very advanced telescopes, measuring a planet's position from light years away leaves you with uncertainties of millions of kilometers, and that's the killer. Those uncertainties grow as you project forward in time. If your probe is going to arrive 50, 100, 200 years after launch, even a tiny initial error in a planet's orbit becomes a huge positional uncertainty by the time the probe gets here. That's why Atlas's path is so provocative. To design a trajectory that hits Mars on October 3, 2025 at 45 million km, then lines up for Venus in late December 2025 at 30 million km, then sets up Jupiter in January 2026 at 150 million km, you need two things that go way beyond casual stargazing. Extremely accurate, long baseline observations of our solar system from Atlas's origin system. Observations taken over decades to nail down not just the big orbital elements, but also the small perturbations from Jupiter, Venus, and even mutual planetary interactions. That's how you shrink the millions of kilometers uncertainty down to something you can actually navigate to. Serious computational trajectory design, the ability to integrate orbits forward across interstellar distances, and, just as importantly, to integrate backward from the desired arrival, geometry, Mars 2025, Venus 2025, Jupiter 2026, to figure out what launch conditions, approach vector, and arrival timing are needed centuries earlier. That's mission design at galactic scale. Neither of those is physically impossible, gravity is predictable, but both require a civilization that has very good optics over very long times, very patient data collection, and the computational power to run high-precision N-body simulations over centuries. So if Atlas's trajectory is designed, that's what it implies in the background. Not magic, not violation of physics, just long observation, plus high-precision computation, plus a plan made a long time ago. If we assume Atlas was launched from within 50 light-years, we're suddenly in a very plausible neighbourhood. That volume of space contains on the order of a couple thousand star systems, plenty of places for a spacefaring civilization to be watching the sun and planning a visit. At that distance, though, the observation problem is real. To detect and characterize our planets from their side, they'd need very large telescopes, apertures in the tens of meters, to spatially resolve or at least precisely measure light variations from the sun. Long observation baselines, years of continuous or repeated measurements, to recover orbital periods for Venus, Earth, Mars, and especially Jupiter. High-precision radial velocity, down to a few meters per second, to estimate planetary masses and nail down gravitational influences. That level of precision is basically the frontier of what humans can do right now with instruments like espresso and harps, and we're doing it from 1 AU away from our own star. An older or more advanced civilization with bigger space-based telescopes and more patience could make those measurements routinely over decades. Once they have that map, the rest of the story looks a lot like what we already do, just stretched to interstellar scale. Here's the sequence in mission terms. Map the target system. Build an accurate ephemeris for the Sun, Venus, Earth, Mars and Jupiter. Include perturbations. Keep updating it over years to reduce uncertainty. Pick the arrival geometry first. Decide. We want the probe to be in the inner solar system around late 2025, early 2026, because that's when Mars, Venus, Jupiter line up in a way that allows chained gravity assists. Work backward. From that desired arrival window, integrate the trajectory back in time to figure out when the probe must leave its home system, at what velocity, and on what approach vector. Choose the launch window. Just like NASA does for Mars, there's a window, but instead of a few weeks, it's a few years or even decades wide because the probe has to cross light years and still hit a moving target. Too early, and it shows up when Mars is on the other side of the Sun. Too late, and the Venus-Jupiter leg doesn't work. There's still a sweet spot, so the idea that Atlas arrived exactly when Mars was near its ecliptic crossing, then Venus a few weeks later, then Jupiter a month later, that's exactly what you'd expect if someone picked an interstellar launch time centuries ago with the goal: arrive in the inner solar system during the 2025-2026 alignment. In other words, once you assume an intelligent sender, nothing about Atlas's timing looks mysterious anymore. It just looks like mission design stretched across 50 light years. The numbers here are staggering. Travelling from 50 light years away at a realistic interstellar velocity, say around 100 kilometers per second, means a journey lasting roughly 150,000 years. That's not just a long mission, that's a civilization-scale undertaking, and that travel time changes everything. Designing a trajectory for a flight lasting 150 millennia means predicting the positions of planets that haven't even completed one full precessional cycle. Over such vast spans of time, the orbits of the planets are not fixed. Jupiter slowly tugs on Mars, Saturn nudges Jupiter, and so on. Subtle gravitational interactions that cause each orbit to shift by a few degrees per millennium. Over 150,000 years, those tiny shifts grow into enormous positional uncertainties. To model planetary locations that far ahead, you'd need simulations that include not just Newtonian gravity, but perturbations, relativistic corrections, and even the tidal forces of the galaxy itself. The solar system is dynamic, and over geological timescales, it breathes and drifts like a living structure. So if Atlas really did launch 150,000 years ago from a star about 50 light-years away, its creators faced a challenge beyond anything humans have ever attempted. They would have had to observe our solar system across decades or centuries to refine orbital parameters, predict planetary positions over 150 millennia, accounting for every known and subtle gravitational influence, design a trajectory that would thread through those predicted positions at the right moments, and finally launch a probe with a velocity so precise that its error margin over 150,000 years would remain microscopic. For perspective, a launch velocity error of just 1 meter per second, a difference imperceptible to our current engines, would compound over that timescale into a positional error of billions of kilometers by the time the probe arrived. To pull this off, the designers would need propulsion systems capable of flawless precision, stability over hundreds of millennia, and navigational accuracy that surpasses even our best atomic clock-based guidance systems. In human terms, it's almost unimaginable, but in engineering terms, it's not impossible. It's just a level of discipline and patience far beyond our own. Or maybe Atlas didn't leave home 150,000 years ago at all. Maybe it's much younger launched, only a few thousand years ago, travelling with propulsion far beyond anything we've built. If it can cruise at a significant fraction of light speed, say, around 10% of C-arm, then the trip from a star 50 light-years away would take only about 500 years. That's still a vast time span by human standards, but it's manageable for a robotic probe or for a civilization whose sense of time stretches across millennia. And that shorter travel time changes the entire design equation. Predicting where Mars, Venus and Jupiter will be 5 centuries in the future is challenging, but it's within reach of high-precision orbital modelling. The gravitational perturbations that would ruin a 150,000-year forecast become tiny corrections in a 500-year window. Suddenly, the idea of a planned trajectory threading 3 planetary encounters doesn't sound impossible, it sounds like engineering. But to move that fast, Atlas would need propulsion systems far beyond our own era. Fusion drives capable of burning deuterium or helium-3 for continuous acceleration. Antimatter rockets, releasing energy thousands of times more efficiently than chemical propellants. Or light sails, pushed across interstellar space by vast ground-based lasers technology we've only begun to conceptualize. If Atlas possesses anything like that, it wouldn't just explain the speed, it could also clarify the September 7th green emission and the October 29th perihelion event. Those might not be natural outgassing or solar heating at all, but controlled burns or maneuver phases, course correction events timed to refine the trajectory as new data came in. In that scenario, Atlas isn't a relic coasting for eons. It's an active, guided interstellar probe, one that entered our solar system already gathering fresh measurements and adjusting its flight plan in real time. Now we get to the part that's actually testable, the December Venus encounter. Venus orbits at about 0.72 AU from the Sun and completes a lap every 225 days. In late December 2025, Atlas's path takes it to within roughly 30 million kilometers of Venus, noticeably closer than the 45 million kilometers we saw with Mars. And because Venus is more massive than Mars, its gravitational pull will produce a stronger deflection. Based on the approach angle we'll be able to pin down by mid-December, that velocity change could be anywhere from 10 to 30 meters per second. That may sound small, but in orbital mechanics the direction matters more than the size. If Atlas passes behind Venus, that is, on the same side Venus is moving toward in its orbit, Venus will pull Atlas forward in the Sun's frame, giving it energy and pushing it slightly outward. That would increase its orbital energy and help set up a cleaner path toward Jupiter, or even a faster exit from the solar system. If Atlas passes in front of Venus, meeting it head-on relative to Venus's orbital motion, Venus will rob Atlas of a bit of momentum, bending its path slightly inward toward the Sun. That would lower any future perihelion, and is the kind of maneuver you'd use if you wanted Atlas to stay in the inner solar system or make future returns. So the whole story turns on a simple geometric detail. Does Atlas pass ahead of Venus or behind it? And that's the beauty of this encounter. We don't have to guess forever. Observations in early December will nail down the approach side, and once we know that, we can predict exactly how Atlas will be aimed at Jupiter in January. In other words, December is the fork in the road, inward and slower, or outward and faster. And whichever one Atlas takes will tell us a lot about whether this is just a visitor or following a plan. The critical observation here is whether the deflection from Venus places Atlas precisely on course for Jupiter. If it does, if the December Venus flyby adjusts Atlas's trajectory such that the January Jupiter encounter occurs at the perfect distance and velocity, then that's strong evidence of intentional design. Natural objects don't just happen to pass through Venus at the right moment, benefiting from a deflection that sets them up for a perfect Jupiter encounter. Such precision is a hallmark of design trajectories. To illustrate, look at Voyager 1's Saturn flyby. It was engineered to deflect the spacecraft toward Titan, allowing a close, optimal flyby of the Moon. That wasn't a coincidence, it was planned, just like Atlas's trajectory would be if it's engineered. If Atlas's Venus flyby accomplishes the same for Jupiter, redirecting its path toward a carefully timed encounter, the parallel to Voyager becomes undeniable. This is mission-level design, not random chance. Avi Loeb has also modelled some potential outcomes for the Jupiter encounter, depending on how Venus deflects Atlas. Let's consider one scenario. If Venus deflects Atlas inward by about 20 MeS, and the Jupiter flyby happens on the inbound side of Jupiter's orbit, roughly 150 million kilometers from the Sun, then the combined effect could slow Atlas by 80 MeS. What happens then? The net result would be that Atlas's velocity drops below escape velocity, meaning it could no longer escape the Sun's gravity. instead of slingshotting out of the solar system, Atlas would be captured into a bound orbit around the Sun. That would make Atlas a permanent resident of the solar system, bound to return to the inner planets on a long elliptical orbit that takes it closer to the Sun every few years. In essence, Atlas could become one of us, an interstellar object-turned-solar system inhabitant. If this happens, Atlas's path would be an engineered trajectory, not a random event. The precise alignment, the careful Venus deflection, the Jupiter encounter, it all points to the same conclusion. This was designed from the start. If Atlas is designed for observation, we could witness additional activity during the upcoming Venus and Jupiter flybys. This could include phenomena like another green glow similar to the one observed on September 7th, perhaps indicating a propulsive maneuver or some kind of course correction. We might also see brightness fluctuations, which could signal attitude adjustments as Atlas reorients itself to target instruments at specific celestial bodies or features in the solar system. There's also the possibility of deliberate transmissions radio signals that might be broadcast back to Atlas's origin civilization, or potentially even forward, transmitting observations to destinations within our solar system. These signals could be the first direct proof of the object's intended mission, a subtle but clear sign that Atlas is actively transmitting data. To detect these activities, we need to monitor Atlas across all wavelengths: radio, optical, infrared, especially during these upcoming planetary encounters. Right now, telescope networks around the world are preparing for these observations, and they will be crucial in revealing any hidden capabilities that might not be detectable through imaging or spectroscopy alone. The critical December observations are already underway, and within the next few weeks we'll begin to piece together the puzzle. By December 20th, we'll have a solid understanding of the Venus flyby geometry. By early January we'll know the specifics of the Jupiter approach, and by late January, after the Jupiter encounter, we'll have a definitive answer to whether Atlas stays in the solar system or slingshots out toward deep space. These observations will determine the fate of the natural hypothesis versus the design hypothesis. If the encounters are random, we'll see no significant trajectory changes or systematic adjustments, just a chance flyby with no grand plan. But if the design hypothesis holds, the encounters will be coordinated, producing clear and predictable outcomes consistent with a mission's objectives. In other words, we're about to find out whether Atlas is curiosity from the stars or part of something much more deliberate. The data will speak for itself. If you've stayed with me through this deep dive into orbital mechanics, probability calculations, and the implications of trajectories that just shouldn't exist by chance, consider liking and subscribing for more explorations into the mysteries that challenge our understanding of what's truly natural and what's engineered. I'd love to hear your thoughts in the comments. Do you think Atlas's triple flyby is a random coincidence, or mission architecture deliberate design behind every move? The numbers are clear, the alignments are precise, and in just 6 weeks, when Venus bends Atlas's path toward Jupiter, we'll finally know the truth. Are we watching an accident of celestial mechanics, or are we witnessing the execution of a plan designed centuries ago by minds we've never met? The math only works if it's deliberate, and if it is, then everything we thought we knew about our place in the cosmos is about to change. Sweet dreams, explorers.